Let's jump right into how engineers took literally the most untamable force in nature and somehow turned it into the ultimate industrial tool. Seriously, if you've ever watched lightning split the night sky, you know you're looking at raw, unbridled power. But what actually happens when you capture that exact same energy and force it through a pinpoint nozzle to slice right through solid steel? Well, here's our roadmap for this explainer. 1. Taming the fourth state. 2. The physics of constriction. 3. Plasma versus laser versus oxyfuel. And 4. The fabrication champion. First up, taming the fourth state. Because to understand how we can cut through solid steel like it's hot butter, we really have to get a grip on the science of what we're actually cutting it with. So think about this. We all learned the basics back in school, right? You add heat, solids turn to liquids, add more heat, liquids turn to gas. But what happens if you just keep pushing energy into that gas? What happens when you superheat it so much that its very molecules actually start breaking down? It becomes plasma, the fourth state of matter. And honestly, this is where the physics gets completely wild. Plasma is not a solid. It has zero melting point and doesn't hold any shape. It's definitely not a liquid, since there's no surface tension or boiling point. It literally contains more energy than a standard gas can even hold. The molecules get so insanely excited that they just start radiating intense light and thermal energy. It is exactly the same stuff that lightning is made of. And when I say intense thermal energy, I mean intense. By mixing electricity and gas, a commercial plasma system whips up an arc that hits a staggering 20,000 degrees Celsius. Just to put that into perspective, that is significantly hotter than the surface of the sun. And it's being generated right there in the palm of a fabricator's hand or mounted on an automated table. No big deal, right? Which brings us to part 2, the physics of constriction. Because look, having all that solar-level heat is completely useless if we can't actually control it. This is where the mechanical engineering of the torch comes in, and it's absolutely brilliant. A plasma system doesn't just create a spark and call it a day. It maximizes efficiency by constricting that high-temperature arc. The consumable parts inside the torch physically squeeze and direct that wild plasma. The gas flow acts like a shaping tool to melt the material, but it also works as a high-powered exhaust, violently blowing all that molten metal right away from the cut edge. It's honestly a fantastic surprise when you really stop and think about it. I mean, you can't just capture pure lightning in a cylinder. You can't put a raw flame in a jar and carry it around. And yet engineers somehow figured out how to shoot this totally uncontainable fourth state of matter out of a handheld nozzle directly at rusted metal precisely on command. And for modern automated manufacturing, oh, it gets way more precise. To achieve what the industry calls high-definition or precision plasma, the arc is put through a really intense 3-step gauntlet. First, high-flow vortex nozzles actually spin the gas. Second, high-velocity mixing chambers compress it. And third, magnetic fields squeeze it even further. This drastically dials up the energy density. We aren't just making a hot spark here, we are literally manipulating the fourth state of matter to give it a razor-sharp edge. Okay, so now that we've tamed the lightning, let's put it in the ring against its 2 biggest industrial rivals. Welcome to Section 3, Plasma versus laser versus oxyfuel. You can essentially think of this heavyweight industrial battle as fire versus light versus lightning. Oxyfuel relies on chemically generated heat, fire, reacting with red-hot metal to turn it into oxide slag. Laser, on the other hand, uses light, specifically coherent photons that melt, burn, and completely vaporize material. And then we have plasma, using lightning, our super excited high-energy arc. If you're running a manufacturing plant, you really have to weigh these options. Lasers, they are incredibly fast and produce gorgeous cuts, but pretty much strictly on thin materials. Plus, they are by far the highest cost to buy and maintain. Oxyfuel, super cheap, but man, it's slow. Plasma hits this incredible middle ground. It's the absolute fastest method available for materials up to about 2.5 inches thick. And here's the real kicker, prep work. Lasers need perfectly clean material. Oxyfuel needs preheating and a surface totally free of rust and dirt. Plasma, almost zero prep. It is highly tolerant of rust, oil, and paint. When you actually map out the optimal business sweet spot based on material thickness and production volume, a massive territory emerges where plasma completely dominates. Sure, lasers carve out their niche in very thin materials at high volumes, and oxyfuel handles those low-volume, super thick jobs. But plasma? It handles the vast majority of mild steel, stainless, and aluminum applications out there. It just gives you the optimal mix of cut quality, productivity, and operating cost. Which tees up our final section perfectly, the fabrication champion. Because the real question is, how does all this theoretical physics and high-end mechanical construction actually translate to dollars and cents for a fabrication business? Well, here is a staggering breakdown that might just blow your mind. When you look at the total operating costs for cutting equipment, power is just 2%, gas is 4%, replacement parts and torch consumables, 6%. A massive, whopping 88% of operating costs are tied up entirely in human labor. And because plasma acts like lightning, it totally attacks that 88% labor bottleneck. It easily blasts right through painted, dirty, oily, and rusty material. No preheating required, so your operators aren't just standing around waiting for metal to get hot. It cuts way faster. And because that highly constricted arc creates a much smaller heat-affected zone, it requires little to zero post-cut grinding or secondary rework. You basically just point your tamed lightning, make the cut, and move right on to the next job. It really is incredible to think about how far we've come since the 1960s when this technology first got off the ground. We literally took the wild, untamable energy of a thunderstorm, constricted it with gas vortexes and magnetic fields, and revolutionized heavy industry to drastically lower human labor costs. It kind of leaves you wondering, doesn't it? Will the fabricators of tomorrow ever find a fifth state of matter to harness? Or is tamed lightning the absolute ultimate manufacturing tool? Just something to think about the next time you drive past a heavy steel structure. Thanks for joining me on this explainer, and I'll catch you on the next one.